All right, so welcome to Chapter 7, Organic Chemistry. I did pull a few slides from Chapter 6, um, kind of just because we're talking about reactions, and Chapter 6 does a lot talking about a bunch of different reactions and reaction intermediates and reaction energy diagrams. And so what I've done, since we're not really doing Chapter 6, I pulled out um, the reaction parts that would be applicable to Chapter 7. Okay, so we're going to be doing substitution reactions. So the only reactions we've done so far is the acid-base reaction. So we've done acid and base reactions, and so in those acids and base reactions, you had to determine, okay, so we have two compounds here, and those compounds, these are reactants, and then we have to predict what a product would be. Well, so this is a typical reaction, and then we predict the products, and so then you label this as an acid, and this is a base, and then we make that a plus, this is a minus, and then this is going to go, and these are the curved arrows, and that makes water, and then sodium chloride. And you learned that if this is the acid, this is the conjugate base, this is the conjugate acid. You learned also with, particularly for acid-base reactions, that the pKa determines which way the equilibrium would go. It's going to go to the highest number of pKa values, which is your weaker acid. So this is a reaction, and this is particularly an acid-base reaction, but the important thing is that you also see that these are the curved arrows. And then those electrons go to the chlorine, and we have stuff like that. Okay, so this is a reaction. Well, now we're going to embark on substitution reactions. And substitution, the atom or a group of atoms are replaced by another group of atoms. So here the Z is going to get replaced by Y. And so you're going to find that this is a nucleophile and this is an electrophile. And you see how I do this. Instead of writing out the word nucleophile, which we introduced that in the Lewis acids and bases, and this is electrophile, you'll see me write an electrophile like this. And it's because you typically have a delta positive, delta negative, some kind of dipole in an electrophile. So the carbon is slightly positive. And then the nucleophile, you're typically going to have some lone pairs or a negative charge, some kind of electron density, and in this case, the nucleophile will quite possibly do curved arrows like this, where Y now has replaced the Z. And so we're not going to be talking about this type of substitution, because you'll find that this is called nucleophilic um, uh, nucleophilic carbonyl substitution, acyl, yeah, acyl. That's the word I was looking for, acyl substitution. This is organic too. Okay, so this is another reason why I'm only pulling out slides from chapter 6 that are pertinent for this next group of reactions. This we will be talking about though. And this we're gonna see an SN1 type reaction or a SN2 type reaction. The S stands for substitution. The N stands for nucleophilic. And you're going to see that the 1 means unimolecular. And this is going to be kinetics. And you'll learn about that. And the 2 here is bimolecular. And so you're going to classify different types of reactions. We just saw where an acid-base reaction is about a proton, and it's a proton transfer. In this case, you have a nucleophile and an electrophile. This is a dipole, and you end up having a substitution. And so you'll see that this is a leaving group. You'll see me just do LG leaving group. And so that's the leaving group. This is the nucleophile because it does the attack like a nuke. And this is your electrophile. This is your leaving group, and this is your substituted product. And you'll see that these substitutions are always on the carbon here. That's what we care about. And you'll need to label them. A reaction mechanism is a detailed description of how the bonds are broken, and a lot of times you learn this in Gen Chem with Hess's law. That was your first introduction to reaction mechanisms. Here, a one-step reaction is a concerted, so you'll hear me talk about whether this is a concerted reaction. You'll see SN2 is a concerted reaction, and you'll have to know that, and that means there's just going to be one step. Your acid-base reaction, where you just had the arrows going from your base to your proton. That was that would be kind of like a concerted. You'll just have these two arrows, curved arrows for a concerted reaction, and it's like a concert. When you go to a concert, you might have clarinets and drums and everything's going at the same time. That's what it means by concerted. So bonds are being broken and formed at the same time. It's one step. It's happening one time. A stepwise reaction mechanism, so SN1 would be stepwise, and something happens first and then something happens second, and you get a reactive intermediate. And so you're going to see something like this, where an SN1 reaction, the leaving group's going to leave, leaving group leaves, and you get a carbocation. This is a reactive intermediate. And then now you can have like, well, would you have iodide? We could have iodide. Iodide comes in and adds, and that's how you get a substitution. So you make something different from the starting material, but you get this reactive intermediate. And you're also going to see, we'll do reaction energy diagrams. And so you're going to have energy here, energy here. This is the reaction progress. Reaction progress. Now in a concerted reaction, you're just going to have something like this, where this is your starting material. This is your product. Hopefully you can see that that's an exothermic reaction from Gen Chem, because your product is lower in energy than your starting material. And then this is your activation energy. And so to get to that top, you just have this one hill to overcome. Just one, and this is an SN2, reaction energy. For an SN1, you got two steps, so you might have something like that, where once again, this would be your starting material. This would be your product. Since product is lower, this is also an exothermic reaction. But now you have this valley, and in this valley is your intermediate. And so here's the carbocation intermediate. And you have two activation energies. You have that one, and then you also have this one. And this is a stepwise reaction. The 1 and the 2 mean something different. It's really about the kinetics. And we'll talk about that. So regardless how many steps there are only two ways to break a bond. You can have the homolysis in each atom. This is radical reactions. They generate radicals. You see, that's called a radical intermediate. This is going to be organic 2. So we won't talk about homolytic cleavage. We will do heterolytic cleavage. And so you'll see in homolytic cleavage, you have these half arrows because you got 2 electrons in this bond, and these half arrows mean 1 electron is going to the A and 1 electron is going to the B. And these are going to be uncharged. But like I said, these radicals, this is free radical chemistry mechanisms, and we're not doing that in organic 1. We are doing heterolytic. So that means when these electrons leave, we get a double-headed arrow because that means both electrons are going, and they're going on to one of the atoms, and that makes that a negative charge, and it leaves the other one with a positive charge. And so this is just showing you the different types of, this is homolytic cleavage with radicals here, and this is going to be important because this is going to be what we see in SN1. The leaving group leaves, and those electrons go with the leaving group. That's why it's negative with its lone pairs here. And then that leaves the carbon as a carbocation. This is going to be organic 2, where you get a carbon anion. So we won't see that in organic 1, but this is something we will see in organic 1. So we're going to look at carbocations, and so you do have a Pogel exercise that talks about carbocations, and that's a carbon surrounded by 6 electrons. When bonds form, they have to have 2 electrons, and so when you have free radicals, which we're not going to talk about in organic 1, they come together. Here, the nucleophile is going to bring both the electrons. This will be the nucleophile. This is the electrophile. Okay, so the arrows. Hopefully you understand double-headed arrows means resonance structures. We've done that in chapter 2. Reaction arrow, this is an irreversible reaction. This is what you're going to see in what we're doing now with SN1 and SN2. They will all be just a one-way arrow from starting material to products. And then you've also seen the double equilibrium arrow. That's what you get in acids and bases. In order to understand which way the equilibrium goes, you have to compare the pK values of your acid and your conjugate acid. But these are all going to be one-way arrows. One more thing, these, and this is the other one, you're going to do the full-headed curved arrows, and it's going to show the movement of electron pairs. You did this in the resonance structures, and now you're going to have to do this here. The half arrow, the fish hook, that's going to be for radical chemistry. So you're learning a language. Oh, okay, so that's all I wanted to pull out from chapter 6. We're on to chapter 7. Okay, so just kind of a little question here. What type of intermediate is in the following reaction? And so you're given your reaction, and then you see the intermediate. This is your intermediate. So hopefully you can see that that's a carbocation. Now, this is a stepwise. So this is going to be an SN1 reaction. It's going to be stepwise. So the energy and reaction progress is going to look like this, where you have a starting material, and then so this is your product. So you made an ether, and you started with an alkyl halide, and your intermediate is this carbocation. Okay, now, so other things I want you to be able to see is I want you to be able to label things. So this is stepwise because you have a carbocation, you have an intermediate, and you see you have what happens first. This is your leaving group, Br, and it leaves, and it's taking those electrons with it and generates the carbocation. So this becomes the negative, and this is your nucleophile. Well, it's not your nucleophile. Here's your nucleophile. The oxygen here, this is your nucleophile. The nucleophile then takes its electrons and goes to the carbocation and makes that new bond right there. You see, we still have that proton on there. And then the bromine's going to do a deprotonation. And so you get HBr and you get your ether product. Now, your goal, you're going to be given something like this. And then you won't have any of this. You have to be able to predict the product, the major organic product. Major organic product, folks, are the ones that have the carbon. So you have to be able to predict the major organic product. You need to be able to label nucleophiles, electrophiles, solvents, leaving groups. You need to be able to label these. You need to be able to show the reaction mechanism. So we're talking the curved arrows here, these curved arrows. Okay, you need to be able to do that. And you need to be able to determine what's the mechanism. And this mechanism is SN1. Okay, so what types of substrates, functional groups, undergo substitution, nucleophilic substitution? Nucleophilic substitution. That's what alkyl halides do. Okay, and so what is an alkyl halide? It has to be an sp3 hybridized carbon. And so the halogen typically can be X. Fluorine is not going to leave. You'll get bromine, you get iodide as a leaving group, Cl as a leaving group. These are the three that are going to, halogens that are going to leave. And you can also need to be able to classify these as primary, secondary, or tertiary. Depends on the number of carbons. So here, F is not going to be a leaving group. F is not a leaving group. Even though it is an alkyl halide, it's not an F leaving group. So here, this is a secondary because this carbon is bonded to two carbons. So that's bonded to two carbons, so it's a secondary alkyl chloride. This carbon is bonded to three. 1, 2, 3. So it's a tertiary. And fluoride is not a leaving group. Okay, so types of this is a vinyl halide. These do not undergo nucleophilic substitution. Why? Because nucleophilic substitution are an sp3 carbon, and I'm going to put leaving group, okay? Because you're going to learn other leaving groups besides just Cl, Br, and iodide. You're going to have other leaving groups, but the one thing that has to stay the same is the carbon has to be an sp3. This is an sp2 carbon. This is an sp2 carbon. This is called a vinyl halide. This is an aryl halide. And these are unreactive in these substitution, nucleophilic substitution reactions. So these are very reactive. So you're going to have to look at your substrate. Your substrate for these are going to be your electrophile. And you're going to have to be able to rank the reactivity in an SN1 reaction and an SN2 reaction. They're going to be different. So allylic halides and benzylic halides are both the fastest in both SN1 and in SN2 reactions. So this is kind of bizarre because it's a little different. Then you're going to see that these have different reactivities for the electrophiles. But allylic halides, you have an sp3 carbon between the leaving group and the sp2 carbon. So this is an sp3 carbon with a leaving group. That's an allylic halide. This is an sp3 carbon. And then here we have an sp2 carbon next door. These are going to be very fast. When we're talking about SN1 or SN2, we haven't talked about what the 1 and 2 means. We're talking kinetics. Okay, so we're going to go back to maybe some Gen Chem 112 and kind of relate the kinetics. So we're talking about fast. So we're talking about the height of that activation energy. The activation energy determines how fast a reaction is going to occur. Okay, so like I said, this is your electrophile. The alkyl halide is the electrophile. They're polar. There's a dipole there. This makes the carbon slightly positive, which makes it your electrophile. And that's why these work. So your nucleophile then can come in with its electrons, and they usually come in from the back side here for an SN2 reaction, and then it pushes out the chloride to leave. So that would be your leaving group. And it's all because you do have this dipole. Physical properties of alkyl halides, they typically have van der Waals, so they're going to have low boiling points. They're heavier than a carbon, so they're going to be a little bit higher than your typical van der Waals alkanes, because they have some polarity. So they're going to have higher melting points and higher boiling points than alkanes. But they're still pretty low. They're going to be soluble in organic solvents. They're going to be insoluble in water. So these are nonpolar. The electronegative halogen creates a polar bond. Like I said, this doesn't leave, but the polar bond makes it a little bit longer and pulls those electrons towards itself in that bond. This creates an electron deficient carbon, and that's what we want. We want that carbon to be electrophilic. Remember, we're doing organic chemistry. We care about the carbon. We want to make carbon-carbon bonds. So we're going to learn reactions that make carbon-carbon bonds or carbon functional groups. So we can change the functional groups. Now, I spent about 6 years doing R&D, research and development at Eli Lilly. And I would say about every week I was doing some form of SN2 reaction. Okay, so this is because we needed to change our functional group in order to make drug molecules. All right, so here we have a nucleophile, and here we have an electrophile. We have a nucleophile. And we're going to substitute the X. X is your leaving group with the nucleophile. So, and then that's what we're going to do here. This is elimination. Okay, so we're also going to talk about elimination reactions, and then we'll talk about elimination, these alkenes, as starting materials in the last part of the course. But elimination reaction, these make elimination reactions. So what's an elimination reaction? This is when you'll learn that this is your alpha carbon, because it has your leaving group. And then you'll see that this is your beta carbon that has the hydrogen. And so if a base, you know, a base looks like a nucleophile. Do you see that? So this is your base. You know, sodium hydroxide is a strong base. But you also know that this is a nucleophile, because nucleophiles have lone pairs and a negative charge. Now, what determines this OH to be a base instead of a nucleophile? Well, if your OH attacks the carbon, and so if this is an OH and it attacks the carbon, that means it's a nucleophile. That's what determines its nucleophile. However, if it goes and gets a hydrogen, that makes it a base. So this is the reaction mechanism. You see I have 3 curved arrows to make this alkene. Okay, which of the following compounds will not undergo a substitution reaction? Well, this is going to be very fast for both SN1 and SN2. This one's going to be fast as well. See, this is your sp3 carbon, sp3 carbon. This is an aryl halide. This is an vinyl, no, allylic halide. So these are super fast. This is a tertiary. See, that's a tertiary. So you want to classify these because you're going to have to determine which will go SN1 the fastest versus SN2. So these are both SN1, SN2. You'll see that um, a tertiary is one of the fastest for an SN1. So that a tertiary is the fastest, and no go for SN2. So they won't go SN2. So this only does, and it's pretty fast for an SN1. This is a vinyl. See, that's an sp2 carbon. So that will not undergo substitution. So that's the 1-bromo-propene. This one, what is this? This is a tertiary. So tertiary would undergo SN1, no go for SN2. So this is SN1. And then this, you will find, what would that one be classified? Is the carbon bonded to any carbons? No, this is a methyl. Okay, if it had been bonded to one carbon, it'd be a primary, secondary. Methyls go super fast here. Methyls are super fast. Okay, fast, super fast. No go for an SN1. No go. So this is SN2 only. Those are the things you're going to have to kind of chart out for your chapters. Which of the following is a nucleophile in the following reaction? Okay, so you want to be able to recognize that this is an, I'm going to go benzyl halide. This is a benzyl group. This is sp3. So this is your electrophile. And this is your nucleophile. Remember when you get sodium, you just go ahead and make that a negative. And you want to kind of draw out your Lewis structures because you're going to have to do your reaction mechanisms for all your open response and Pogels. So this is your nucleophile. And so that's your electrophile. And this one will do both SN1 and SN2. So remember this is concerted. Concerted, like a concert, one step reaction. This is going to be stepwise. So you're going to get a carbocation intermediate. So I told you benzyl halide can do both SN1 and SN2. This will be an SN2, and I will teach you how to know that. The reason why is this is a strong nucleophile. That's a strong nucleophile. Strong nucleophiles always undergo SN2. So when I say always, you better write that down. It's hard to get scientists to say always. All right, so now this bromine is your leaving group, and now it's being substituted with an OH. And so we just changed our functional group. Our starting material functional group is a benzyl halide. You could say benzyl bromide. And our product is an alcohol. And it's a benzyl alcohol. So these make great functional group transformations. A transformation is when we change from one functional group to the next. So what's the nucleophile? Sodium hydroxide. Substitution reactions. All right, you have to have three components, as we've been talking about. An sp3 hybridized carbon, this is your electrophile. A nucleophile, and a leaving group. And you need to be able to label those. So here, this is a primary, this is a secondary, and this is a primary. Now all of these are strong nucleophiles. How do I know it's a strong nucleophile? A strong nucleophile has a negative charge. If you see a negative charge, it's a strong nucleophile. Do you see the negative charge? That makes these strong, and that makes them an SN2 reaction. So because there's a strong nucleophile, these are going to go SN2. Now, and they're concerted. You see how I'm drawing my mechanism right now. Here's that, and there's the mechanism here. Now, these are your leaving groups. This is concerted. That's why we have two curved curved arrows. Notice that none of these are tertiary alkyl halides. The tertiary alkyl halide will undergo SN1. These are all SN2. Okay, so you have to be able to determine whether you have a strong nucleophile. So once you find your nucleophile, you need to decide, is it strong? Is it neutral? Or is it weak? Well, just weak. How about strong versus weak? This is strong. Negative charge is strong. So a negative charge nucleophile like hydroxides, thiols, are always going to have counter ions. And so when you recognize these counter ions, which are metals from the group 1 or even group 2, the alkali and the alkaline earth metals, you make them positive. And then that will tell you got a negative charge. Neutral nucleophiles. I'm going to call them weak. Okay. Weak nucleophiles because they're still nucleophile because they have a lone pair. You got to have a lone pair to be a nucleophile, folks. Okay. So here we have a lone pair. So, and then it's going to go to the electrophile, and then this is your leaving group. This is a primary. You want to classify your electrophiles. And sometimes it's called a substrate. A substrate has the carbon of interest. Okay, so you want to classify these because they're going to help you know whether this is SN1 or SN2. This is an SN2. You see how you have two curved arrows and there's no intermediate. Drawing products. You need to be able to draw products. So here, this is a primary. This is your nucleophile. And it's going to be an SN2 reaction. And then you went from an alkyl halide to an amine. And you see how you got a functional group transformation? The leaving group. The leaving group, we're going to look at the leaving groups, and then you have to decide, do you have a good leaving group? Do you have a great leaving group? Okay, if you have a great leaving group, the reaction is going to be fast. If it's an SN2. And it'll be faster if it's an SN1. So let's look at a leaving group. Water is a better leaving group than OH. OH is not a good leaving group. Not a good leaving group. Okay. Water is a great leaving group because, you know what? Water is very stable. You know that. Water's everywhere. But OH is not very stable. And so what makes a good leaving group, what makes something a great leaving group? It's got to be stable on its own. Stable when it leaves. It's like, why do people break up in a relationship? Is, you know what? If the person feels stable on their own when they leave, they're going to be great leaving groups. Okay? So you can think of these molecules. Water is stable on its own, so it's going to be a better leaving group. So So water is a better leaving group. Ammonia is a great leaving group because ammonia is a neutral. Do you see how these are neutral molecules? There's no charges. These are stable. Iodide is a great leaving group. And that's because it's just so friggin' big. It's like the Buick, the station wagon. You remember the station wagon of the 70s and the 80s? That's Iodide is the Buick of cars, okay? It's just big. Fluoride doesn't leave. It's too small. It will not stabilize the negative charge. So here's your different leaving groups. This is going to be a great leaving group because when it leaves, it goes neutral. See, it becomes water. Iodide's a great leaving group as well because it's big. And you can look at the pKa values and see a trend here. So this does not want to become HCl. Okay, so it's -7. So they're going to be weak acids are going to be your best leaving. Conjugate bases of weaker acids are poor leaving groups. So, well, it's even worse. So these are, I guess your stronger acids are going to be better. I don't know, water's great. Ammonia's great. Hydrogen's great. Hydride is not. So this is it's because it's a conjugate base. OH is a bad leaving group. NH2, they have the negative charge. H minus. These are horrible leaving groups, okay? Just horrible leaving groups. Fluoride's a horrible leaving group. What is the strongest nucleophile? Okay. What do you think, folks? Draw it out. If you're having trouble still, you need to go back to POGA 1. Okay. So that is a secondary alkyl halide. You'll find that secondaries do SN1 and SN2. So it's going to depend on your conditions. Okay. So what is this? This is an electrophile, folks. Water. There's water. Water has a lone pair, doesn't it? So it can be a nucleophile, but it's going to be neutral. How do you know there's going to be a neutral nucleophile? Because no negative charge. Methanol. This is methanol. It has a lone pair, so it is also a nucleophile, but it's going to be a neutral or weak. I'll say weak because there's no negative charge. Sodium cyanide. Well, there's your sodium counterion. If you draw your Lewis structures, you would see that this is the Lewis structure. You need to practice Lewis structures, and that means this is a strong nucleophile. And strong nucleophiles undergo SN2. What is the leaving group? Well, this is your electrophile, right? This is your nucleophile. There's your leaving group. Okay, so nucleophile and bases, they're very similar. They both have a lone pair. Bases will attack protons. So they go after the H3O plus. They go after the proton. Nucleophiles will attack usually the carbons. That's what you care about here. This is showing you if you have a nucleophile, it's going after the carbon. If it's a base, it's going after the proton. And you're going to see that when your nucleophiles go after your beta hydrogen, B is for beta, that's going to be an E2 reaction or an E1. It'll be really an E2. You won't have E1 on that. So E2. So basicity is a measure of how readily an atom will donate its electron pair to a proton. Nucleophility is how readily the atom will donate its electron pairs to Let's focus on carbon. Um, so we're looking at these different nucleophiles, and um, you can look at them like this. Um, OH is a stronger base, so therefore it's going to be a stronger nucleophile. I think fluoride is not a good nucleophile. That creates some problems. This is a great nucleophile because, you know, the carbon does not want a negative, so it will do anything to get rid of the negative. Nitrogen, negative. Notice they all have negative charges, okay? They do not want to be negative. So if it picks up a proton, then it becomes neutral. NH3, H2O, CH4. Okay, so we have a stronger nucleophile is small. Um, so if they're smaller, hold on for just a second. Okay, so it's smaller, and that's going to make sense because you don't want steric hindrance. Okay, so the reason why, think about it, the nucleophile wants to form a bond with the carbon. So if it wants to form a bond with the carbon, then it needs to be able to get into the carbon. And so if it's really small, it can actually get in there without steric hindrance. Now we've talked about steric hindrance. Here, tert-butoxide, these methyl groups are rotating around like those big propellers that you might see out in the west, and they're just really big. Well, that's what's going on here with this free rotation. Okay, and so it makes it really hard to actually get that negative backside attack. And I keep saying backside attack. Okay, backside attack is kind of like when you're hitting a baseball and you're sitting up at the bat and you got your bat and you're waiting to hit the baseball coming at you. Okay, you have to make contact. In order for this lone pair to come in with the carbon and make a bond, it has to make contact and it has to come in to a certain proximity, and it actually ejects the leaving group. So it's kind of like the ball. Now, tert-butoxide is a base. It is not a nucleophile. Okay? It's just too darn big. It's not going to ever get in there and make a covalent bond. So it's going to take a proton any day of the week. Where are you going to find protons? Well, you got protons out here. I mean, it's going to take a proton, and then you're going to make an alkene. Ethoxide, sodium ethoxide, you'll see it like this. You'll see it like this. That is very small. It's not sterically hindered, and it will make a great nucleophile. Solvent effects. Okay, well, you can have polar protic. There's three types. You can have polar aprotic, or you can have non-polar solvents. Non-polar solvents are like hexanes and benzenes and carbon tetrachloride and hexanes, dichloromethane. Okay, these are going to be non-polar. Polar protic are going to be like water, methanol. These are polar protic. They have a hydrogen bond bonded to an oxygen. Polar aprotic will be like DMF, dimethyl formamide. Dimethyl formamide. DMSO, dimethyl sulfoxide. So these are Also THF. THF is tetrahydrofuran. You might want to get some of these down and classify them because they'll be helpful in solving problems. These are polar, so they'll stay, remember like dissolves like. So these will dissolve sodium hydroxide, right? Sodium cyanide, because those are polar, but they're going to be better for SN2. This is going to be better for SN2 because you don't want the protic, you don't want a hydrogen. You will find that polar protic is great for SN1. So polar protic, you want methanol, water, they're going to stabilize a carbocation. It's all about stabilizing that intermediate for an SN1. Solvation by polar protic solvent. So this is polar protic, so I'm thinking SN1. And so what happens is the oxygen will stay with this negative, will stabilize the positive, and then the hydrogen bonds will stabilize the nucleophile. This is your nucleophile. So polar protic solvents, these are polar protic solvents. Get some of these in your notes. You'll need them. Polar aprotic solvents, get these in your notes. They have no OH or oxygen nitrogen bonds. So these are some great examples of polar aprotic, which are going to be important for SN2 reactions. These are the kind of solvents you want. Polar aprotic solvents can solvate the cations. They end up making a naked, more reactive nucleophile. So remember, I said in SN2, what do you want? You want strong nucleophiles. Remember I said always? Well, if you have a polar aprotic solvent, it's going to even make your nucleophile stronger. Increase in nucleicity in polar aprotic solvents. So here's the negative charged nucleophiles. You'll know that these are considered strong. They all have negative charges, and you want polar aprotic solvents for these because they're going to make them even stronger nucleophiles. Neutral nucleophiles, when we think about these are weak. These are weak nucleophiles. And they have lone pairs. So if you drew them out, you'd see that they have a lone pair, but they do not have a negative charge. These are great for SN1, and you would want polar protic solvents. So stuff like methanol and water, because that's going to be great for your stabilizing a carbocation. So which compound is the better nucleophile? Better means stronger. Okay, so this would be weak. This would be weak. This is a base, folks. Remember? This is going to be a base because it's sterically hindered. And then we have this one, CH3 and H. So this is going to be your strong nucleophile. Bond breaking and bond making in nucleophilic substitution reactions. So here the sigma bond is broken and the sigma bond is formed. And the nucleophile substitutes the leaving group here. So does the bond making and breaking occur at the same time? That's concerted. If it does, it's an SN2 reaction. If the bond breaking occurs first, you're going to get an intermediate. And that intermediate for these reactions is going to be a carbocation. And this is stepwise, so that's SN1. Bond making occurs first? Bond breaking occurs first. Does your bond making occurs first? Um, so here, this is SN2, and it's concerted. And that means your bond being broken and made happens at the same time. So this is one, and it's bimolecular. That's what the 2 means. The rate, and that means the rate depends on concentration of both. So when you do your rate law, remember the K times, this would be the concentration of your nucleophile and the concentration of your substrate, your electrophile. And so you can actually do kinetic experiments when you change the amounts, the concentrations of each of these, and it will affect the overall rate. So it's second order. So that's what the 2 means. It's bimolecular. And it's about the rate of the reaction. Okay, this is SN1, and that means the rate of your reaction depends, it's unimolecular. It only depends on one concentration, and that's the concentration of your substrate. Okay, so your substrate, the carbon containing, or your electrophile. So the rate depends on the leaving group leaves. So if you have a great leaving group like iodide or something that can be very stable on its own, like OH2, okay, because when it leaves it becomes water, that's going to generate a carbocation, and then your carbocation will be attacked in the second step by the nucleophile. This is going to be SN2, and this is a methyl halide because the carbon, the sp3 carbon, is not bonded to any other carbon. So this is SN2. Remember, what's the rate for SN2? You have allylic, you have benzylic, they're fast, you have methyl, then you have primary, and then you have secondary. So those are the rates for an SN2 reaction, bimolecular. This is, okay, so this one's first order. This is a tertiary. Remember, for SN1, you have allylic, you have benzylic, you have tertiary, and then you have secondary. You don't have any methyl, you don't have any primary. So the first thing that happens is the leaving group leaves, and you get a carbocation, and then your nucleophile will come in to form your product. That's unimolecular. So how do you draw the reaction mechanisms? You use the curved arrow notation, and you need to have 2 curved arrows. And you're telling a story. You're saying that the bond breaking and the bond making occurs at the same time. That's concerted. Things, you know, the drums and the clarinets and the flutes are all concerted in a concert. They're all happening at the same time. And so this is SN2 because the rate of your reaction depends on both the nucleophile concentration and the electrophile. This is your nucleophile. You see you have a strong one. It's negative charge. And this is your electrophile. And you get a new bond made. So these are your kinetics. They're bimolecular. And this is your reaction energy diagram. And you just have the activation energy. I'm not going to make you draw a transition state, but in this transition state you see that this is showing you that it's backside attack, meaning on this plane the bond being formed and the bond being broken to the leaving group is in the same plane on the backside. And that's going to be very important for an SN2 reaction. But you don't have an intermediate. Because remember, the SN1 reaction, you have this intermediate. So because you have a carbocation. But you don't have that here. This is an SN2. Which compound reacts the fastest with sodium methoxide? Okay, well, what's sodium methoxide? Sodium methoxide, you might see it like that. You got to know this in different ways. So, and then whenever you see it, you might want to draw your structure like this. So this is a strong nucleophile. All right, now let's draw these. 2-butene, 1, 2, 3, 4, 3 bromo, 2-butene, 1, 2, there's butene. Butane, 2 bromo, butane, 1 butene, 2 bromo, 1 bromo, butane. Okay, so 2 bromo, 1 butene. This is an sp2, no reaction. 2 bromo butane, that's a secondary. This is 2 butene, 3 bromo, so this is an sp2, no reaction. Excuse me for my cough. And what is this? A primary. So this is a strong nucleophile. And so strong nucleophiles want to undergo SN2 reactions. And what's going to be faster? A nucleophile, your electrophiles for an SN2. Remember, they're allylic, they're benzylic, they're methyl, and they're primary, and then they're secondary. So this is secondary, this is primary. Primaries are going to go faster for an SN2 reaction. Stereochemistry of the SN2. This is the backside attack, folks. And this is important. Stereochemistry means we need wedges. So whenever you have to show stereochemistry in a reaction, concerted reactions, if you have a dash or a wedge, some kind of stereochemistry in your substrate, this is your substrate, the carbon-containing electrophile, then, and you have at a stereocenter a reaction, then you need to show it in the product. So that means you got to draw a dash or a wedge. And this is for concerted reaction. So SN2 is concerted reaction. So what's happening is you don't draw it like this, okay? It's backside attack. So you need to actually draw the nucleophile coming in across from the bromine, and then the bromine leaves. So this is front side attack, doesn't happen, folks. That doesn't happen. Backside attack, it comes in to this anti-orbital backside on the plane, and the bromine leaves. Now what happens here is you get an inversion of stereochemistry. Now you might not see that because you got this wedge, it's still a wedge. But let's do it. Let's assign that stereochem. Well, you'll see an example. You'll see you get an inversion of stereochemistry, which usually means that the R becomes the S and the S becomes the R. So they're showing you this here. The nucleophile comes in, and oh, well, there's a nucleophile. So this is important. Let's just read it. All SN2 reactions proceed by backside attack of the nucleophile, and you get inversion of stereochemistry at the stereocenter. They're going to be in enantiomers. So they're showing you the transition state shows these partial bonds being broken and formed because the nucleophile comes in at the backside attack. This causes inversion of SN2, and so I need to see, when I see your mechanisms, that you draw it from the opposite, the backside attack. The bond to the nucleophile in the product is always on the opposite side compared to the bond to the leaving group. The rates of reactivity for an SN2 reaction, methyl primary, tertiary doesn't even happen. And then also I want you to go ahead and put the allylic and benzylic up here with the fastest reactions. And that's because of the steric. So if a nucleophile can get into the backside attack to this carbon, it's going to when it's least sterically hindered. So you can see here, this is rotating around. This is going to knock it out. It's kind of like defense. Okay, it's going to knock out that nucleophile every time. It's not even going to happen. Secondary is hard enough. And these are about rates of reaction. Which one? Which one wins? SN2 versus SN1? It's the one that happens the fastest. Okay, so we're talking about rates of reaction. So the characteristics of an SN2 reaction. Second order. One step, it's concerted. Backside attack, so you better show inversion of configuration. Configuration is R versus S. And the nomenclature of a stereogenic center. Think of dashes and wedges. We're dealing with sp3 carbons. Unhindered halides react the fastest. Also include the allylic and the benzylic in there, because halides. I wouldn't even put tertiary in there. SN2 reactions in drugs. So here we have that leaves, and then this also comes out and leaves, and you get that compound here, SN2, and that makes Prozac. And that wraps up chapter 7.